In this video, we're going to look at how to do a technique called implicit differentiation. So the technique is implicit differentiation. So basically, given an implicit equation, we'll be able to differentiate that equation implicitly. So given an implicit equation, so here we have r of x, y is equal to 0, we can actually differentiate this equation with respect to either variable implicitly. So the following will be how to differentiate implicitly with respect to x. So to differentiate implicitly with respect to x, we do the following. So you always have to choose a variable that you're differentiating with respect to. So if you're differentiating with respect to x, you're trying to solve for dy dx. If you're differentiating with respect to y, instead of having dy dx, you'll have derivatives that look like dx dy. So the dy will be in the denominator because you're differentiating with respect to the y variable instead of the x variable. So first you always want to choose the variable that you're differentiating with respect to, and you always need to be consistent for a given computation. So to differentiate with respect to the x variable, we do the following. So first is we take the correct view of the equation. So in our minds, we need to think of the variable y as a secret function of the variable x. So think of the variable y as a secret function of x. i.e., view y as y of x. So in your mind, when you see a y show up in the equation, you think of it as y of x, a function of x. Now, we previously discussed how with these implicit equations, y is not truly a function of x because the graph of the equations usually does not satisfy the vertical line test. Nevertheless, we use something what mathematicians call implicit functions. So we think of y as an implicit function of x. Now, before I mention why this is not good terminology, because y is not a function of x at all. It is appropriate to say that y is locally a function of x because local, the word local means that only near the point that you're of a given point. So if you look at the graph and you just take a little bubble around that point and say, in this neighborhood, y looks like a function of x. You can do that, and that's what an implicit function of x is, hence implicit differentiation. But just to be less technical and to avoid tricky terms, let's just think of it. Y, you just have to think, it's a mental mindset. Y is a secret function of x. So when you see y appear in the equation, think of it as secretly representing a function of x, even though truly it's not a function of x. Second step, we differentiate the equation with respect to x using just ordinary derivative rules with a couple of caveats. Any term that contains an x is differentiated as normal. X cubed becomes 3x squared. Sine of x becomes cosine of x. ln of x becomes 1 over x. So a couple caveats, any term or factor of a term containing x and x alone is differentiated as normal. Two, whenever you see a y, you have to go back and think of y as a hidden function a secret function of the variable x. And so if y is a secret function of x, in order to differentiate an expression involving y with respect to x, we have to use the chain rule. So whenever a factor in a term depends on y, we differentiate using the chain rule. That is, we take the derivative with respect to y and then multiply that derivative by dy dx. Right, so if you have y cubed, the derivative is 3y squared dy dx. So basically, whenever you have a term or a factor that contains y, just differentiate it, y cubed, 3y squared, and then correct by multiplying it by dy dx. So it's 3y squared, but I'm taking the derivative with respect to x, not with respect to y, so I throw in a factor of dy dx to correct for that. And then if you have a term that has a function of x times a function of y, just use the product rule. When you're taking the derivative of the function of x, you take the derivative as normal. When you're taking the derivative of the factor that's a function of y, you take the derivative with respect to y and then multiply by dy dx. In the end, when you're finished, you obtain basically an algebraic equation in the derivative dy dx. So the result is always a linear algebraic equation in y prime, or dy dx, if you will. So y prime, aka dy dx. And you can always solve a linear equation. So you might have nonlinear functions of y and x still cropping up, but it's going to be something times y prime plus something is equal to 0, so you can solve it for y prime, and that is the implicit derivative of y with respect to x. So we'll do a simple example here, and then we'll do some slightly more complex examples in our next video. So the simple example is just for the circle x squared plus y squared is equal to 1. So let's choose a point on the circle. Some point that is on a unit circle. So how about x is equal to 1/2, y is equal to root 3/2. So this certainly satisfies the equation x squared plus y squared is equal to 1. Yeah, 1/2 squared is 1/4. Square root of 3/2 squared is 3/4. 1/4 plus 3/4 is equal to 1. So let's try to find the tangent line to this curve at the point 1/2 square root of 3/2 using implicit differentiation. So that point right there. Okay, so to differentiate this implicitly, we just differentiate as normal. So we're going to differentiate implicitly with respect to x. Differentiate implicitly with respect to the variable x. So to achieve this, we just differentiate term by term as always. The derivative of x squared is 2x, right? So the derivative of x squared, 2x, plus the derivative of y squared. So here we're going to view y as a secret function of x. So we secretly think of it as y of x squared. So now the chain rule comes into play. The 2 comes down, we get 2 y of x to the first power times the derivative of the inside. So instead of y squared, we get 2y times dy dx. and then the derivative of 1 is just equal to 0. So when we differentiate the equation x squared plus y squared equals to 1 implicitly, we obtain the equation 2x plus 2y dy dx is equal to 0. Now it's probably a style preference, so you can write it this way, or you can write 2x plus 2y y prime is equal to 0. So you can write the derivative either as dy dx or as y prime when you do this. It doesn't make a difference, they both represent the same thing. Notice that this result is linear in the derivative, so it's linear in y prime. In other words, each term either contains no factor of the derivative or just a single factor of the derivative, dy dx. It's something plus something times dy dx. So if you think of dy dx as the variable and x and y as constants, it's a linear equation. Or this is equal to, it would look like a linear function. So to solve this, we're going to subtract off the 2x to the other side, and then divide by the 2y. So dy dx is going to be minus x over y. The 2's cancel out. So here's the derivative as it depends on both x and y. So this is important because when you have an implicit equation, it's the variable y is not a function of x at all. Right? We can see this with the circle. For a given x value, you can go to that y value, or you can go down here to that y value. Now obviously the slope is going to be different up here than it is down there, because here the slope is decreasing and here it's increasing. So depending on which point you are on the circle, you're going to get a different slope. Even if you have the same two points with the same x value, you need to also specify the y value to have the derivative. So this is basically the local derivative in the neighborhood of one of the points on the graph. So when you're evaluating the derivative, first you want to do a quick check. Does my point satisfy the original equation up here? So yes, the point 1/2 comma root 3 over 2 does satisfy the equation x squared plus y squared is equal to 1. Okay, so this does represent a point on my graph. Very important. Now let's do the slope. dy dx is equal to minus x over y. So the derivative at this point, dy dx, is going to be minus x, so that's minus 1/2, divided by y, root 3 over 2. The 1/2s over 1/2 cancel. This cancels with this. So we ultimately just get minus 1 over square root of 3. Another way of writing this is y prime at the point 1/2 comma root 3 over 2 is equal to minus 1 over root 3. So this notation will be y prime as a function of x and y is equal to minus, well, is equal to this, which is then evaluated at minus 1 over root 3. Now we have a point right here, and we have its slope, so we can compute the tangent line and see if we're correct. Well, so let's compute the equation for the line that passes through the point 1/2 comma root 3 over 2 with slope of minus 1 over root 3. Well, the point slope formula can be used. Y minus y naught is equal to slope times x minus x naught. So here y is going to equal y naught. Y naught was root 3 over 2 plus the slope is negative, so minus 1 over root 3 times x minus x naught, like that. So there's the equation of the tangent line. Now to see if this works, here was my plot of the circle, x squared plus y squared is equal to 1. Now let's add to that the second equation, square root of 3, let's just say y equals square root of 3 over 2 minus 1 over square root of 3 times x minus 1 over 2. So I'm going to plot both of these concurrently, and let's make that one red. So you can see that here's the point 1/2 root 3 over 2, so that's right above the 1/2. And this equation that we just derived is indeed the tangent line to the circle at that point. So pretty cool thing, right? We didn't have to solve for y as a function of x. We just differentiated implicitly. Just take the derivative as you normally would. The only kick is treat y like a function of x. So instead of just doing 2y, you have to do 2y dy dx. So if you didn't do that, you would have 2x plus 2y is equal to 0. Well, that can't be true because 2x plus 2y equals 0 is not the same as x squared plus y squared is equal to 1. You can't satisfy them both. So doing the 2y dy dx, you can solve for dy dx and get the derivative that way.